Hello, everyone. Welcome back to another lecture on intelligent systems. So this time we are going to have an introduction to machine learning. Now, for those of you who have already taken a machine learning course or maybe the AI course, most of what we'll do today you already know. The main reason for having this introduction here is that there is no prerequisite on machine learning for the intelligent systems course, and we'll need to have at least some basics in machine learning for what we'll do in the upcoming lectures. So if you already did a machine learning course, then again, you can go through most of it pretty fast, I think. Otherwise, I'm going to give you a quick introduction on machine learning, on the most important concepts, and then to have a bit of applied machine learning knowledge, we're going to look at some machine learning algorithms and how they can be used for clustering, classification, and making predictions. Finally, we've already started looking into evaluating machine learning systems last time, so we'll continue with this time and learn a few more evaluation metrics and methodologies. So to also clean up where machine learning fits into the overall AI landscape, well, AI is basically the main theme. So AI covers everything, artificial intelligence, including things that we have done in this course, like knowledge graphs, natural language processing, but also other concepts that we don't have in this course, but for example, in the Introduction to AI course, things like game playing, state-space search, and so on. Now, a subcategory in AI are algorithms that learn based on data. So these are machine learning algorithms. They don't just appear in AI, for example, in data mining, which you know when you did work on databases, you also do a lot of machine learning. So machine learning is used a lot in AI for various applications, but it's not limited to just AI. So machine learning is a subfield of AI. And then the hip topic that everyone has been talking about for the last couple of years is deep learning, which is a specific kind of machine learning. Actually, you could further subcategorize it because a subcategory of machine learning are neural networks, which we'll also talk about later in the course. And deep learning is kind of the modern version of neural networks. So very roughly, this is how these terms fit into the overall landscape. And you can also see the rough timeline. So AI started somewhere in the 1950s with the first, with the definition of the term and the first algorithms. Remember, we looked at ELIZA, the very first chatbot. Machine learning as a discipline started really taking off in the 1980s. In the 1990s, we had the first neural networks, but the modern version of neural networks, the deep learning techniques, have really become popular in the last 10 years. So machine learning itself, as a term, goes back to the 1950s, proposed by Arthur Samuel, and he defined it as a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P, if its performance at task in T, as measured by P, improves with experience E. So you can see the core definition of machine learning. We have something that we want to do, some task, for example, predicting or classifying some data. The algorithm itself learns by looking at data. What it does, we talk of training the algorithm, is it builds a model using the data. And once we have built a model, we can use it to predict new incoming data. So machine learning can be understood as a kind of automated reasoning, meaning a kind of automated inference. We talked about inference before, so that's the process of deriving new facts from a set of premises. And you can do this derivation in different ways, and here I'll briefly introduce deduction, abduction, and induction. So of these three, you'll see that deduction is the only sound, the only correct way of doing inference. Deduction is also known as natural deduction. So here, the conclusion follows necessary from the premises. So we have a premise like A, and we have given that A implies B. And from these two pieces of information, we can conclude that B must also be true. So what we do is we conclude from the general case to a specific example of that case. And the famous example going back to Greek philosophy is all men are mortal, Socrates is a man. And then from 1 and 2, we can conclude that Socrates is mortal. So here you can map this to the implication. If something is a man, then that something is mortal. Then we have a specific example, Socrates. And then from these two together, we can conclude that Socrates is mortal. This is also the kind of deduction that we used when we did subclass inference in RDFS, for example. Now we have a person, and then every student is a person, and then we could make these deductions, create these new triples using natural deduction. Another way of doing reasoning is abduction. So here the conclusion is one possible explanation for the premise. So we do it kind of the opposite way around. We have A implies B, we know B, and now we conclude that A must be true. So to give an example, we say that drunk people do not walk straight. We know that John does not walk straight. And from these two pieces of information, we conclude that John must be drunk. So you can already see that this is not a logically sound, not a logically correct way of doing reasoning. But it's one possible explanation we can give. And even though it's not logically sound, not mathematically strictly correct, this is something we do in real life all the time. For example, in medicine, what we do know is that a disease causes certain symptoms. But this is not the way doctors work. Yeah, when you are sick, you go to the doctor, you complain about some symptoms, and then the doctor has to conclude back to the disease. Otherwise, it would be easy. You know, you don't go to the doctor and say, hey, I have the disease so-and-so, and the doctor tells you, okay, because of that disease, you now have system high fever and system runny nose. It's just the other way around. But you know that this can go wrong. Yeah, there can be other reasons, not just the ones that were listed there, and then you can make a wrong conclusion. And finally, we have inductive reasoning. So basically here we have a few specific examples, and then we try to, from these examples, make some general rule about a class. For example, we have that A and C together implies B, and A and D together implies B. So now we say, okay, in both cases we have A, so A implies B must be true. So again, let's look at an example. We could say that all computer science students in Comp 474 are smart. Then all computer science students on vacation are smart. And therefore, from these two, we just conclude that computer science students must be smart in general. So again, you can see that this is not sound. This is not logically, mathematically, strictly correct, but it's one way to make a hypothesis or generalize from some given examples. And this is in fact what we do most of the time in machine learning. because we give the system a lot of examples. In many cases, the examples are labeled as positive or negative examples. And then we use this to give to a system to learn from the examples. And basically the system tries to look at these examples and extrapolate how to classify a new instance that it has never seen before. So classification, for example, you want to give the system an image, and then the system has to say, what is on this image? Is it a dog? Is it a cat? Is it Elon Musk? So you give lots and lots of training examples to the system, where you tell the system with a label what it is. So you give it 100,000 examples of cats, of dogs, and of Elon Musk. And then the system learns how to recognize those. And then when you give it a new image that it has not seen before, it can give you a prediction for the class. So you can see, or you can understand machine learning as giving the system a lot of data. And what the system is trying to learn is basically a function to separate the data. So here we have, let's say we look at two-dimensional points. Remember, we talked about vector spaces and dimensions last time. And I said we'll often simplify to 2 dimensions or maybe 3, because this is something we can draw and visualize. In real life, again, we would have hundreds of thousands of dimensions in real machine learning. So again, here for the example, we have 2 dimensions. We just look on an image and look at length versus color. And then we have all the green dots, which are images of cats, and we have all the red dots, which are images of dogs. Now you can see that the system can try to learn a function. This is the green line here, to separate all the samples in one class, the dog samples, from all the samples in the other class, the green samples. So this line here is a decision boundary, and it separates our samples into 2 decision regions. So in 2 dimensions, the boundary would be a line. In 3 dimensions, it would be a plane, and so on. Of course, this is not the only possible boundary. You could have an algorithm that learns a more complicated one, like the blue one here. It does the same thing. It separates all green samples from all the red samples, but it's a lot more complicated. So very often in machine learning, it's not just the question of finding any kind of boundary. You also want to find one that has certain properties. For example, you could say, I prefer a simpler, smoother boundary. In machine learning terminology, this is called an inductive bias. So saying I prefer a simpler separation to a more complicated one. This is inductive bias. In these cases here, you can see that both separate these samples perfectly. So in our evaluation, they would have 100% accuracy. But you can see if you now present a new sample, for example, a new dog picture, and let's say it falls here, then the green line would clearly say this is a dog because it's on the other side of the decision boundary. It's here. But looking at the blue line, if the new sample is here, it would actually classify it as a cat. So this is the first, first, the reason for having this kind of inductive bias, and second, the reason we talk about training versus testing later on. So to be able to do machine learning, you have to feed in the data. And the first step that's happening is to extract features from the data. In the example here, you can see we are feeding in images of cats and dogs, but all the system sees are 2 features color and length. So there is a step where we decide which features we want, and this is going to be our input data. We already talked about vectors and vector space model last time, so you are kind of comfortable with the idea of representing data in form of a vector. Last time we had vectors of, for example, tags to classify movies, and we could use a similar feature vector here, but this is not limited to the vectors we had last time. For example, if you want to feed in emails, you could have features like the length of the email, the time it was sent, the domain it was sent from. So each of those could be a feature. So basically a feature vector is a list of attribute value pairs. For example, length of the email, 1 kilobyte. So these attributes is something that's fixed. This is something you decide before. Each attribute has a number of possible values. And then what we end up with is an n-dimensional vector space, now just like last time. So we can represent images here in 2 dimensions. We can represent an email in 3, 4, 5, whatever dimensions, depending on the feature vector that we decided here. Then you feed this feature vector into a machine learning algorithm. And there are lots and lots of algorithms. So I'll show you a few, but some examples you might have heard of are probabilistic methods. Naive Bayes classifier, for example, is widely used in spam filtering. So when you have your, when you're training your own spam filter, yeah, the one in your email client, and you say this is spam or this is not spam, very often this is using a naive Bayes classifier. You've seen decision trees. Decision trees are basically a big if then else tree where you come from the starting point to a decision, to a classification at the end. And you have probably heard about neural networks where we have lots of simple processing units, but a lot of them. And then we put these together to make, for example, the classification decision, like cat versus dog. We'll talk about neural networks in one of the later lectures. There are also different kinds of machine learning algorithms. So one that we'll use a lot, and that's also one of the very common ones, is called supervised learning. Supervised learning because when you show the sample data to the system, you need to have a label with each data sample. So you teach the system what the correct input is. For example, here we show the system images of Tom and Jerry, and each input sample is labeled with the correct class. Then you feed this into your algorithm. The algorithm is going to build a model. And then the model, you can give a new image. And because it learned these labels, it can assign a label to the new data. So in this case, either Jerry or Tom. Or on the example of an email spam filter, it would be spam or ham. So that's supervised learning. And what you need to be able to do supervised learning is data with a label. The opposite is unsupervised learning. You simply give the system a lot of data, and then the system itself is trying to discover some patterns in the data. So in this case, it could group these examples together in so-called clusters. And then because you don't have a label, it can actually not give them a name. Now it can just group these together and these together because they look similar. But it cannot say that this is Tom and this is Jerry because it never learned these labels. So in unsupervised learning, you only have unlabeled data. You can still train the system, but you cannot expect a kind of label like we had before. A third kind of learning is reinforcement learning. And this is something you need where you cannot make a decision right away. In all of the examples before, we had sort of a direct reward, a direct feedback. For example, showing an image and deciding is it cat or dog. This is a one-shot process. You show the image, you give the result, cat, dog. But in many applications, this doesn't work. For example, when you play a longer game, you want the system to play chess, Monopoly, whatever you want, then you cannot give direct feedback after the first move. You cannot say, okay, I move one piece, and then this is correct or wrong. You only know at the end of the game, for example, by winning or losing, if this was overall good or not. So reinforcement learning has kind of a long feedback loop where you have a reward at the end, and then the agent learns over time from this positive or negative feedback. As a nice example, have a look at this video on YouTube about an AI trying to learn how to park a car. So this is an example of reinforcement learning because the car starts in a certain position and you cannot say in one step if you made something correct or not. It's a long sequence of turning the wheel, accelerating, going backwards until you're finally in the parking spot. It's quite long, so you might want to fast forward throughout the video, but have a look at the beginning, like the middle, at the end, to get an impression how long it takes for the AI to learn how to park the car. And I'll see you back in the next lecture part.